live. Just the link I'll share.
Yeah. There you go. It makes the math for you that better. Actually, yeah. No, that's the whole thing.
Probably one of these. Do both of those.
Don't work.
Okay.
Unless, of course, you extend it to this in a more complicated shape. Well, yeah, it's kind of like, suppose you look at the integers. One way to look at it is just, okay, they're discrete things. But what if you look at a sine wave and look at what the sine wave crosses the thing? And you go, oh, well, it's more complicated structure, even though, it looks more complicated. It's just, discrete, so whatever intersects are, kind of lengths, maybe you just see that it goes over the clouds. So you can make it a little bit more complicated in some sense. Yeah, exactly.
Guys, just so you know, we are broadcasting live right now. So we're just going to have the background up. We will start in about 2 minutes. I'm just going to tweet the links to the Hangout so everybody can join us. And then I will do some introductions and we'll get started. And we'll make sure everybody's in the room. Oh, we need the judges. They might be here. Joel, Frank, will you get the judges and tell everybody to get in here, please?
Do you want me yeah, but we don't need it. They're going to be plugged in straight. I was going
Do we need more chairs? Yeah, I guess we need more chairs.
So we're just supposed to be use the calculator.
No, they're lots.
Right there. We are right.
One more thing over here.
If I do a touch something, we'll get out. Attention in there.
Ready for game day.
Okay. Ladies and gentlemen, welcome. So very excited to have all of you here today. This is the inaugural year for us. The NASA Global Space Apps Challenge has been going now for 5 years, first time in Tampa. So excited that we had a nice event this year. Almost 50 people registered. Of the 60, we formed 1, 2, 3, 4, 5, 6, 7, 8 successful teams who submitted pitches. I'm going to announce the order that they're going to speak. Team All Your Space will be first. Team Musk, Team Anabolic Astronauts, Team Spartan, Team Thinkamingo, Team Rocket, Team Feliday Tech. We'll wrap this up. If you have a PowerPoint, we'll need one person in the control area in the back to advance your slides. Your speakers will be up here. You'll be able to see what the audience sees right there. This is a live event. Please keep that in mind. All ages audience, including our live audience, so please be aware. And I'd like to welcome and thank our judges. Mr. Wes Baylor, he is a member of Tampa Hackerspace and also a member and leader of Team Miles and the company Fluid and Reason. Callie Burke, she is from Kennedy Space Center. She is an engineer with the Launch Services. Thank you for coming over. Armando Burke, who is a legend. He helped us in so many ways, including providing the great space that we're at. We're at SoftWorks in Ybor City, so thank you so much for coming. Without further ado, I want to please invite Team All Your Space. Come on up. Let's hear what you got to say. Pitches are 5 minutes. And if you're going to be bringing a laptop up for your presentation for the PowerPoint, please make sure you get it to Kayla before you're announced so she can get you plugged in. Thanks.
I'm just going to trade. Love prototypes. All right, so make it go to video. We've done this before. Which settings is it display? Not seeing this at all. Oh, there it goes. There we go.
Yeah.
All right. Okay, so my name is Tracy Birch, and we are Team All Your Space, and we did the Space Route 66 Challenge, which was about building a future spaceport and looking at the future of multi-use facilities at NASA. So we decided to do a little physical game here. And what this is going to be is there will be a map with perhaps the existing Kennedy Space Center land on it. And then we'll have physical building blocks, like a little toy play set. The difference being that when you So when you put the building blocks onto the map, then this would have a chance to have multimedia, audio, video, images, text of each building as they're placed on the play surface. And this could, of course, be extended into virtual reality. It could be constructing a virtual reality setup of the map you're constructing, as well as more information, more in-depth information depending on the target age. This could be set up for younger kids, for adults, for as much depth as you want to go into. And you know, we've got the wildlife refuge. We could have the different vehicle assembly and maintenance, cargo, passenger terminals, green power generation. All that could be included. And then with 3D printing and the availability of all the great NASA data and multimedia, as well as private space flight companies and even other people out there, they could add their own 3D print their own blocks and add them in. A nice thing about this is that it could be used separately from the computer. You can sit down on the floor and play with your kids. It could be used by people with physical or cognitive limitations where, you know, clicking and dragging on a traditional app might be difficult, but they can actually use this and then maybe have audio or have an accessible braille display or something with the information about the buildings. And I did this, of course, I've got my 3 kids here, Sarah, James, and Catherine back there, as well as our other teammate, Daniel. But it's really great. I get the best ideas from them. You know, I sat down all ready to write a computer program, write some kind of fancy VR app, and then I stopped and said, wait a minute, how about something you guys can play with? And we took it from there. And that's what I've done. Thank you.
Thank you. And I did forget to mention our final team is actually team number 1. There you'll be our final team. Next up, I'd like to welcome
That's happened before.
Team Musk, please. Team Musk. Okay. You want to like leave one of these over there. What? Well, you were going to block it.
Oh, gotcha.
Actually, only need the mouse. Where's the dongle for it? Oh, yeah. All right. While we wait, you want us to introduce ourselves? All right, so I'm John. This is Daniel, Steven. You guys? And second now. Coming up.
There we go.
So we need that. All right. Ready? All right. So we made an application called Valatum, and we were challenged to produce a unique solution while continuing to utilize a high standard for development. And we designed an application to aid drone pilots for the Don't Crash My Drone Challenge. Next thing. Actually, just go back 1 second. So for our application, we used Bootstrap, Django, Python, and there was one more. Bluemix, of course. And Daniel will talk more about that. Yes, so we did use IBM's Bluemix as the host and to manage our application. The application main purpose is to store and aggregate flight data like terrain, elevation changes, weather information, no-fly zones like airports or government facility buildings, stuff like that, where any drone flight controlling software could easily tap into that just by giving the drone current location, speed, bearing, and return within a 5-mile radius any potential like warnings, dramatic changes in elevation, or if they're approaching any no-fly zones.
So we use Python primarily to develop this project. And one of the reasons we use Python specifically is because it's very easy to use compared to other languages, and it's very popular too. So that would make it a lot easier for other developers out there, or even people that like to tinker with this with drones, to implement pretty much our code and utilize it, make it pretty easy for them to use.
Yeah, it's pretty good for like rapid development, very easy for hobbyists to use, stuff like that. So that's a feature. And so we extracted our weather data from openweathermap.com. That includes wind speed, cloudiness, pressure, humidity, and temperature. We also used Google Maps API for terrain data to sense difference in terrain and elevation with the drone. We used openfly.org to collect no-fly zones. That's about it. And if you guys want to see a live demo of the project. So this is sort of a front-end implementation of our back-end database that we developed. This is somewhat prototype, somewhat finished. So that's small about. And then, so like if you were using this for personal, this would be where the map would be, and you would maybe put like a drone view to the side. But as an example, here we have live data pulled from our database when you navigate to the website. So it pulled that you're near Tampa International Airport, and it gives you the latitude and longitude and tells you it's a potential no-fly zone. And this is a Python script that we just ran to make a virtual drone, and we just marked its location as here. So that's something that you can do. So like people would register their drones, and it would tell you, oh, there's drones nearby. So that's one great invitation. That's just done with the Python script, I guess. And that's pretty much it. You got any questions? Do we still have time?
We're doing questions for all the questions. So is this is the website, or is the back is this an attachment any current drones?
No, because we didn't really have any drones to like put it on or anything like that. We only have 2 days, so we just made a virtual drone, and we just marked it here. And we just manually entered it into our database.
And could you guys show some of your previous slides? I couldn't actually see them.
That's fine. It's still open. Or do you have to hit start? Yeah. Did it come up? Yep. So anyone in particular?
And just this one and the next one, I couldn't see the text for.
Good. You want to go through them anyway?
Those ones I got.
No, your demo you showed us was just an HTML file on the local machine. We're able to.
No, it's not HTML. It's the Django. The Django generates the HTML, and like we sort of just generated a front end implementation. So like this stuff was like done in Bootstrap, right? So we generated the code for Bootstrap. So what? Oh, is PowerPoint still on?
No, but anyway, did you get live data coming from these APIs?
Yes. Yeah. Okay. Yeah. So like, I'll just flip it around for you. So like, this is just template for now because we couldn't get the Google Map API to work and we don't have a drones view. But this stuff is straight data pulled from the database. So like this international airport was stored in our database as a potential no-fly zone. And that was something we pulled from openfly.org. So anything else? We good? All right, thank you.
Awesome, thank you guys. All right, next up we have Team Anabolic Astronauts. Come on up.
So we actually don't have a visual, but I'll talk it out. I'm Aaron Iglesias. This is my teammate Christine Manastersky, and today we're going to be discussing the Astrosize project, which is dealing with the issue of minimizing muscle breakdown and bone breakdown in astronauts in space. After doing some research, we realized that there are some flaws in their diet and workout routine currently. Specifically, their macronutrient intake is 17% protein, 34% fat, 51% carbohydrates. However, competitive athletes on Earth are typically around 50% carbohydrates, 25% fats, 25% protein. And that extra protein intake is critical for minimizing muscle breakdown as well as synthesizing new muscle. Specifically, the most important amino acid is leucine, which is primarily found in eggs and whey, neither of which astronauts currently intake. However, they can intake this through branched-chain amino acids. And we think through supplementing branched-chain amino acids in between their meals, they can synthesize new muscle, minimize muscle breakdown. And the great thing about branched-chain amino acids is that they're powderized, so it will preserve its freshness in space. And that's about it for diet. As far as their workout routines, I do realize that their workouts are pretty heavily treadmill, which is great for cardiovascular health. However, for gaining new muscle, it's not the best. We think that more compound movements such as kettlebell swings, chest presses, and pull-ups are ideal. And of course, in space, you can't do kettlebell swings, right, because you don't have weight. However, what you could do is clamp the astronaut's feet to the ground, and using resistance bands from the back, you can actually simulate it. And that works because you're using tension instead of gravity. Same deal with pull-ups. You can design a vest, and the vest can tie resistance bands to the ground, and they can simulate a pull-up, right? Chest press, you can be on the ground, clamp the astronaut to the ground, and use your resistance bands to push up, and that'll work the chest and triceps. And that already covers a lot of the muscles in the astronaut's body. There's new technology that recently came out called the shape scale. Now, the shape scale is you stand on it, and an arm actually comes out of it and gives a 360-degree scan of your body, and it tells you not only how much weight you've lost since you last weighed yourself on it, but it also gives you the proportions of muscle and fat that you've lost on your body. And what we could do is actually implement that technology for astronauts in space. Obviously, you can't gauge how much weight they're losing, but you can gauge the proportion in which their muscles might be atrophying, right? And that can actually be sent to a trainer on Earth, and that trainer on Earth can recommend new workouts for the astronauts, right? I think that's it. Thank you.
Thank you, guys. All right, next up we have Team Spartan. Did you get your print?
I did not, but I've got notes. So okay, so you just, yeah, I think I can set it up.
Let's see how this works. Awesome. Yeah. Thank you. Just 1 second, guys. All right, so my name is Wayne, and I'm a team of one presenting Team Spartan with Training with Buzz, social workouts in space. The challenge that I attempted to solve was the same one that you guys just heard, which was astrocyze, how to help astronauts keep their bodies fit, which in turn helps the mission and helps everyone. So, a little about myself. I love working out. It feels good. It's good for you. And I think we all know the benefits of having a strong body in general. But sometimes I succumb to laziness. I make an excuse to skip a day, then I skip 2 days. My metabolism begins to slow. My thinking becomes cloudy. And this is really, really just annoying. But to our friends in space, this is more than just annoying. It can be life-threatening. So through my research, I found that astronauts as well also have this problem of keeping to their regimens. Only about 75% of the time do they actually keep to their scheduled routines. And this is the outcome. So on the left, we have normal vertebrae, and on the right, we have the outcome of not working out and applying load to your bones. This is bone mineral degradation, and it's the worst outcome of long exposure to low space. So my solution is Training with Buzz. So it combines workouts and a social atmosphere to incentivize astronauts to get back up there and lift that weight. So I'm going to talk through two components, the actual app and then the connected equipment, which will help connect the folks in space with us folks on Earth. So also from my research, I found that social influence, positive recognition, and reciprocity have a positive impact on how much people are willing to exercise. And we all kind of have this in the back of our mind, like, we all want to work out, buddy, go work out with friends, keeps us motivated. But this hasn't really been applied in a rigorous manner to astronauts. And I think having that go up to space is great, because now we have live streaming, people can work out together, and my solution leverages that. So, quick demo of the app, if it comes up. So on first load, you have, we're going, are you ready? And this is actually for us on space, the portal to which we connect with the astronauts. So you log on with Facebook. I'm going to bypass all that, go straight to the app. And so this is what comes up. You have your feed, which has everyone around the world who's participating in Train with Buzz. At the top, you see live astral training in T-minus 3 hours and X amount of minutes. So you can be updated on when astronauts are going to train, so you can join in with their training experience. Open up your feed. That's me. I live on the moon, obviously. And if you click astral training, you pop into a session with Mike Hopkins. He actually finished this session. He did the Helos workout, making a personal best of 1846. He says, okay, Earthlings, are you keeping up? So I'm going to move on from the demo and skip through all these slides, which are just in case the demo didn't work. Okay, so more science. So there are already solutions to helping astronauts. There's a great a device called ARED, which is Adaptive Resistance Exercise Device. And what we see on the screen here is on the far right are the degradation of ARED exercises compared to all other exercises that astronauts have tried. So the real important one is the bone mineral. What is that? The bone mineral density of the pelvis is much lower using ARED. So what ARED does is it does compound movements, your squats, your deadlifts, your military presses, your pull downs. And what that does is it compresses your core. And that's kind of like, if you all have, elderly folk in our family, the hips go first, the core bones are the ones that go the quickest. And so what ARED does, what my solution does, is help astronauts get back to training their core. So simplicity, I like this solution because not only can it be implemented in space, but it can be implemented here on Earth, so that not only can you follow along with astronauts, you can do the exact same exercises. So big picture view, you have an app connected to your exercise equipment. And this is kind of the slogan. Training with Buzz combines the science of motivation and the fundamentals of fitness in the pursuit of the final frontier. And so thanks.
Thank you, Wayne. Next up, we have team thinking.
I guess not.
I'm sorry, judges. Please, we're good?
We're good. Good.
We're good. Thank you. I'm German. I like to keep the schedule on.
Okay, so we're Team Thinkamingo, and we did the Bucket to the Moon challenge. I'm Elizabeth. I'm a junior in high school, and I'm a musician, programmer. I was on First Robotics, and I'm an athlete. And there's my brother and my parents who have now been developing apps for 5 years, for 11. Our challenge was the Luna Book one. It was to make an educational app to teach kids why going to the moon is still important and why we need to return. So our app that we came up with was Lunar Locator, which the home screen, it finds the moon based on your location through calculations, and it uses arrows to point to where you need to be pointing, and it is somewhere there, yeah. And then it also includes the phase that it's in right now, and has like an icon of it. We have stories that are like folk tales and poems. The poems have read-along audio with them. And there's the biography of Neil Armstrong. And then we have pictures from different missions around the world. There's like the Luna 2, I think. Apollo something. And we have video to go along with it. It's built into an HTML page. And
That's his new program.
yeah. And so that's the app that we came up with. And for the future, we'd like to expand it to include all of the solar system so that we can have the full set and eventually make it more integrated and fun and engaging for kids. So that's us. Questions?
Anything from the judges? No? Good.
Just
All
out
right,
of curiosity,
thank
does when you're showing it, you show the arrows. Does it tell you whether or not the moon is overhead right now, or on the other side of the Earth, or like blocked by the Earth?
I mean, it points like up or down. So I mean, if it's pointing down, you can tell that it's on the other side.
Oh, okay, so that's how you know.
Yeah.
Okay.
Thank you.
Thank you, bingo. Next up, we have Team Rocket.
Yeah.
It's okay if we launch this year, right?
Does audio?
Yes.
Does audio? Do you have audio on this HDMI? Maybe my computer's too old.
We need.
Is there a way for me to hook this up with the audio?
I think it goes through HDMI.
Yeah, it goes with HDMI.
So if you just plug it in, there's video and audio to the same page.
Right. But I tried playing a sound and that didn't work. Nothing sounded. But I know it's
So she's gonna, I tried her previously and it didn't work for me, so maybe the volume here is kind of. Yeah, someone volume's on here.
It's your, just, never. Yeah, right. So I'm muting it.
I see.
All right.
Let's roll with it.
Rocket sounds.
Yeah.
Afternoon, we are Team Rocket, myself and Christian Stanley, Amber, Jay, Frank, Rhea. Most of us did not know each other or even knew what a hackathon was. Come Friday night, came together. It's been a whole lot of fun. The whole process was we focused on the 3D print my rocket. Why 3D print a rocket? Well, in 2012, it was estimated that the SLS was going to cost $500 million a piece. And that was years ago. So now, with current technologies, and what we wanted to focus on with print my rocket was make it stronger, faster, lighter, and cheaper. We conclude this with that NASA has too much space. Specifically, the fuselage and the fairing, which is manufactured elsewhere and then shipped. This allows us to ship the material and then it be printed on site, whether it's traditional 3D printing or further processes that the experimenter looked into, such as extruding carbon fiber, graphene, and other materials that could be weaved. This is efficient as we'll be able to design specific space per the mission instead of using overall pieces. Specifically for our application this weekend, though, we focused on looking at a leading consumer rocket and then translating it into 3D printability. Considering that this rocket is $18 a piece and this in material is 50 cents. So 5 hours a piece, 50 cents. This is something that we're able to, for STEAM programs, youth groups, it's no longer one rocket for the classroom, it's one rocket for every kid in class. So how we went through our process, we did start looking at the capabilities of the 3D printer, the restrictions of the bed and materiality. We did some testing starting from 0.35 millimeters to 0.55 millimeters, understanding that the nozzle was rated for 1.2 millimeters. We're able to get it down to half a millimeter thick, and it still withstands 7 Red Bull cans on the top without crushing that hinge. So the structural integrity, and as you saw on the launch, the center and axis of thrust was consistent and stable throughout the burn. And even on our second launch, yes, we got to launch this rocket twice. With the C65 engine on the second launch, we did reach over 300 meters, and without a parachute was able to recover within 50 meters.
Yeah. Thank you. And it was able that we were, as you can see, the bottom is threaded, unscrewed, plugged in. It's the same design as this, but some of the benefits with 3D printing is we no longer need the mechanical parts or wasted space that comes with the packaging of this. Everything can be included in one piece, modular. And this we did look at this, scaling it up, what could be put through the future, as well as, again, referencing the alternative 3D printing methods that are in conjunction with today's technology and emerging technologies. We have, for your viewing presentation, our sea rocket firing. Thank you.
If I'm not mistaken, SpaceX hasn't yet recovered the same rocket twice, right?
You gotta stay up all weekend by drinking those Red Bulls.
Oh, do you guys have any? This is actually the one we had fired twice. All right. As you can see, it did come apart in 3 pieces. We noted a few things like using acetone for fusing it, or if we wanted to leave it apart, but it actually came straight down, landed on the asphalt, and bounced. And still fine and able to refire.
Any questions?
No parachute.
No parachute. But it did deploy the top, or it ejected the top, so if we were to add that in later models, we could work with that.
Did you guys glue on the lugs, or did you print that all as one piece?
That's the only piece that had to be added on later because of the 3D print capabilities. Everything else could just be slid on without any fasteners.
That can be resolved in
Okay, so
future
there were-
versions.
So multiple printings, but then that was the only part that had to be attached.
Actually,
using
one print.
Oh, okay, that makes sense. Okay, so like, all right.
It was multiple printings when we were printing piece by piece by piece, but now we've got it down to a 4x8, which is a very standard maker bot. This is something that one go, it's already got the structure included and everything. So it's pretty straightforward. And like I said, overall material is only 50 cents tops.
Okay. Yeah, and that's the $18 for without the engines, right?
And being able to fire, because we were talking with these rockets, usually after 3-4 firings, especially the cardboard bottom, warped, torn. One thing we noticed, as you can see, it is starting to flake on bottom. We thought it was because of the use of acetone, but the way it's printed laterally, you're able to even take, peel, and then just keep shortening the rocket or print another modular piece.
Very cool. Thank you. All right, next up we have Team Holiday Tech.
Oh, we have it in the back.
Yeah,
So do I need to?
I think we have the clicker. Hey everyone, we are Holiday Tech. My name is Alicia,
And I'm Jonathan.
and we're presenting on the backfill problem. This
Fetch the mouse.
Okay, so a little background on the problem. NASA would like to be able to take any of the models, the things they built, and scale them to a version which they can manipulate with your hands, or like convey information, or if they wanted to design something and then convey it on a smaller scale. So that's the solution we came up with. It uses okay. So what are some of the effects that you get from scaling things down? Some of the problems you get is that in issues in models with large extenders like this, if you were to scale everything down linearly, you could lose this type of defined feature. So one of the things you have to do is you have to add extra structure, but you don't want to add so much that it deforms it and it changes the overall impression of the model. But if it is something that extends to such great lengths, as in this example, you want to convey it so you still want to retain some of that information. So just in terms of materials, we noticed that with 3D models, just to maintain the surface integrity, about 1 to 2 millimeters is enough to maintain a good thickness for your structure. It doesn't take into account the scale of your object, so you might need extra support, but just the minimal thickness you want to go is about 1 or 2, or else it becomes quite fragile in the hand, which is something we're trying to avoid. So some of the things that we've taken, so the first thing we do is we want to scale the walls. And that will, so in order to do that, we need to create a uniform wall. Or once we've chosen a thickness for our walls, then we also need to extend that over the entire model. And then,
So we're creating 2 models. We're creating one from the surface of our feature, and we use a uniform thickness for our minimum. The other one, we take if it's got an interior, we scale that down. And so we're going to superimpose the 2 and take whichever is thicker at the walls. So if the scaled version is thicker, we'll take that, and if the uniform wall thickness, so we can resolve some of these feature problems.
And then once we've solved that issue, then we would look more into what sort of internal structure we would need to create in order to give it a good, robust design.
Yeah, so suppose we have a box and we want to exert some sort of pressure, but then we want to scale it down smaller and exert that exact same pressure, but we're only looking at the outside. We can improve the structural formation on the inside to strengthen and provide that same workload. But we'll have to add material, but we can add it in an optimal way.
So just for the wall thickness, the approach we came up with was that if the user would give us a model which had some sort of wall thickness, we would take that into account, but we'd also implement our minimal wall uniform thickness around the perimeter of it, and then we add them together to give it strength or reinforcement where it wasn't, we detected that it wasn't reinforced enough in the original, and also give it that extra structure that we need. Here is more, there are basically 2 approaches to thickening the wall of a surface. This is more for if you have a solid geometry. What we're dealing with is more of a tessellated structure, so something with just bases and it's not solid. The approach here is that you take your solid and then you use another solid in order to get either the combination, which is the union, the intersection, which is where the 2 would have colliding areas, and then, or else you could take the difference, which is where you get the subtractive areas. This is more of what we used because we have bases instead of actual solids. So what you would do is you would add an actual structure to the vertices, and then you'd extend it along the edges, and then we have a better explanation. But basically, you're adding solids to just bases. Here's how it would work. You'd start with each face in your structure. You would add spheres to the corners. You'd extend them along the edges of your faces, and then you'd add a face or another triangle to connect them. And that would result in a thicker wall for all of your faces. Here's something we did where here's the starting model. As you can see, it basically has no thickness. and then we iterate through all the triangles, and then we add those spheres, and you can see that it has a thickness now. Now, one thing you may notice is that it has been morphed. It's no longer the same. It doesn't have as sharp of angles anymore, and it's also larger on the outside. So we would use subtraction, which is another one of the geometric combinations, is that you can subtract the original model from this to get what was added to the outside. And then we would basically just have deformation on the inside. Here's a case that you could have where you have a feature that gets smaller than your wall thickness. What would result is that after you've added the wall thickness, you get distortion on both ends. But like I said before, we'd be removing the original from what was added, and so we would just get thickness on the inside. And we'd still have a minimal thickness, or we'd have a smaller thickness than what we'd want, but we wouldn't get that distortion. Do you have to talk about stream?
Okay, so the previous section was just how to backfill the outermost part to provide some sort of minimal stability. But the process of strengthening the internal object is actually a question about strain, and it depends on how you're using it. So you can actually have the same object. So, for instance, in this figure B, we have the outside is a rectangle. But if we're providing uniform loads to all the sides, the optimal strength to weight minimization is this pattern here with all sorts of little bubbles. But if you look at the first, if you attach the left-hand side to a wall, keep it fixed, and apply a load down on the right-hand side, then this becomes the optimal. And you see if you take your rectangle and do the same thing, you get some sort of hybrid between the two. So it's not just, oh, I have this shape, here's the optimal interior. It depends on what you're going to do with the shape. So if you're going to twist it, and you get, but the general overall algorithm is the same. So you use some sort of physics engine to simulate the force of the solid. There's some open source physics engines. Then you identify the regions within that are under the highest stress. Then you go and look at the low stress areas, remove, take bubbles around it, and shift the material to the higher stress areas. And so as you remove more and more, then you'll shift, and it's an iterative process. But it's fairly straightforward. But there's different ways for optimizing, but they all kind of work with that same sort of idea. So you would take your cat, you would voxelate it, you would just start removing it with the shape optimization. Then you get this interior support. So for instance, this particular one, they're maximizing the strength for if you put pressure on the ears and the nose, and then you can see what the interior comes out with. And then you can 3D print that. So possible applications of that is, suppose you're going to use regolith, suppose you're going to go and 3D print on Mars, and you want to print a building. Well, you might want to optimize that, and also optimize that as far as your strength. Optimizing the strength and minimizing the weight, well, minimizing weight results in how much time it is to print. It also puts less strain, because I guess the regolith has little sharp stuff, so you want to run your machine for as little time as possible. So, and you can use some averaging. So for instance, these previous ones just considered static forces. So suppose you want to consider some sort of force of gravity, but occasionally there's a torsion. So you can do some averaging techniques to not necessarily have the global solution for a static force, but to kind of average out for these other forces too. So you can get some compromises. And we are using these other references for our work. Yeah. I guess one of them's a preprint for a talk that happened last year, so it's pretty new stuff.
Yeah. And then the second one's something that's been referenced to. Mm-hmm. It's basically the same technology. Mm-hmm. So we covered basically two different things. We covered how to generate a uniform wall surface or wall thickness throughout a model, and then we also talked more about how to write an algorithm that maximizes the amount of strength you can get with the least amount of material.
So for your tool, so you talked about what it was doing. So, do you have a tool that's capable of doing some of these algorithms, or these algorithms that you've developed?
So we simulated some of these. We drew and we used Mathematica, but we use that for, I guess, rapid prototyping. You'd want to do something more long-term, like get some sort of C++ or or Python engine that's portable for an open source Mathematica that gets proprietary, but we can make the source code available. But
Yeah,
we'd
just
like
the
to,
wall thickness is a small project.
Okay, so you guys are doing the prototyping.
yeah. But so we wanted to concentrate on describing the algorithm so you can put it in any language.
Yeah.
Yeah, simplify it.
Thank you.
And our final team presenting today will be team number 1.
I don't know how this works, so.
Slideshow. Enable editing.
Just to enable
editing. Enable editing.
Okay.
My computer
Yeah.
from beginning on the left.
Thanks. Okay, so we're team number 1, and what we did was the astrospace one. So when we first started, we had like a lot of ideas going on, and it's named Biospace after a Greek goddess. It uses a combination of heat sensors, EMG biofeedback, and a system for finding the optimal tension and force levels of your muscles. So that's why there's like the muscles in here. And some of the problems that we ran into with the current situation is that there's a substantial amount of weight and the equipment currently used, and there's 3 different equipments that are used for the body. And we also found there was a difference in magnitude and pressure in the different kinds of machines that they use. So we wanted to incorporate some kind of like tension band that could balance that. And there was a loss of tension from the pressure. And this is like the current equipment because they use 3 different ones that are the 3 main ones. A cycle ergometer, which is to measure like your heart rate and all that cardiovascular stuff. And then there's a treadmill, which is used for like walking, and the resistance exercise device, which has a lot of the tension bands already in there, which is like a rubber band like thing where you can use like for your arms, legs, abs, and stuff. Okay, this is what we found for the pressure magnitude for our specific tension bands. And so there has to be a pressure of 58 and a magnitude of 7.35 because to get a certain amount of tension for the muscles so that you will build new muscles. Okay, so in our Biospace suit and machine, this is like a picture of it because there's a little bit of what I do. Whoops. Yeah, it's like touchscreen, which is really weird. Okay, so there's a video we made, but this is just a picture of it. And in the suit itself is the EMG biofeedback and EKG and a heat sensors, so you don't have to worry about
the cyclo thingy jiggy that they already have. And you just have these two devices. And so, and there's also a headset spot for like their music if they want to listen to it. And the secondary application of it involves a series of resistance bands designed to strengthen the muscle and bones and counteract muscle atrophy and bone loss through resistance strength training program. And such training increases muscle strength, tone, and mass. And it stimulates microscopic tears, inciting regenerative anabolic, which is like muscle building. So what happens with bodybuilders when they lift a lot of weights, their muscles tear and then they build muscles. So that should help prevent the atrophy that the astronauts come back with. And yeah, that's it. Oh, I can't get that on your computer. So.
Any questions?
Was your idea both a suit and a new exercise set of equipment, or?
It was kind of like a both, because in the, well, it's not really up here anymore, but in the last picture, they're attached to a treadmill, and the treadmill is connected to a device that straps them down, but as long as it has tension bands as well on the thing. And so the suit itself is what has the EKG, the EMG, and the heat sensors, which help to monitor the heart rate and stuff. So like all the
Great, awesome. Thank you.
Guys, those were some amazing projects. I mean, you know, we've been here for 48 hours. You know, you don't get the full 5 sensory effect of a 48-hour hackathon, but we've been busy. I want to just, let's give all the teams a huge round of applause. This event would not have been possible without a lot of help from a lot of different people. We have a lot of volunteers from Tampa Hackerspace. I'd like to give them a big round of applause. We have this beautiful facility where we held the event, Softworks. Couldn't thank you guys enough for making the space available. Team Reason provided us with the grand prize, the brand new Oculus Rift. We have prizes also donated from Fun with Bots, from Tampa Hackerspace. We received a nice contribution from Jable Blue Sky. Financially, we received several other financial contributions from other companies whose names escape me because I'm in public speaking mode. We did get a nice stack of Red Bull, which kind of fueled the whole event. So I want to thank all of our sponsors for providing that. And of course, Team Miles, who said, hey, why don't we do this at Tampa Hackerspace? Throw this party for us. So thank you guys, Team Miles, for that. Also providing sponsorship as well. Let me tell you what's going to happen now. So we got our 3 judges. They are going to now go and deliberate for the next no more than an hour. I want to be back in here by 3:30 at the latest. Okay? We will be giving a grand prize of a brand new Oculus Rift, the one that just came out. All the team members, so here's what I did. I asked each team to nominate an MVP. Because we only have one Oculus Rift, and some of the teams have more than one person, the MVP gets to decide who's keeping the Oculus Rift, and they can say it's mine. All the other members are going to get an Arduino. We have 3 different models. 2 are wearable. 1 is has snaps to build circuits. 1 is solderable. The 3rd one's a more traditional Arduino. So we'll let the team members pick from those. The top team will also receive, each team member, a year of membership for Tampa Hackerspace. We have 2 additional local prizes where you have a make-block robotic kit can be used to build a moving robot. You can expand it and build a CNC or a 3D printer or really any other type of machine that's built with aluminum struts and motors and servos. And those teams, that team will also have their choice of Arduinos for the secondary members. I say non-MVPs, not to minimize anybody's contribution. 6-month memberships for Tampa Hackerspace. The other team, we have some Blink Blinks that were donated. compliments of the global organizers for the Space Apps Challenge. So we have up to 4 of those to give away. And 3-month memberships for Tampa Hackerspace. While the judges are deliberating for the main prizes, they will also choose 2 teams to go forward for global judging. Oh, one last prize, and I'm so sorry, Callie, I almost forgot. 3 tickets to Kennedy Space Center. 2018. And that will be our honorable mention prize. But we will be able to nominate 2 teams to be put forth for global judging. Winners of global judging will receive I don't know what, but they will at minimum be invited to come watch a launch at Kennedy Space Center. So that's kind of a cool thing. We also are able to put forth 1 team as the People's Choice Award. And People's Choice means you guys get to pick that team. So what I would like to do is have every person write their top 3 choices for the People's Choice Award. And Kayla will collect those. Hi, Kayla. Kayla will collect those. Please get them to her no later than 3:15. Okay? Actually, it's 2:36. 3 o'clock. Okay? And we will collate those and figure out who our People's Choice Award will be. If you are nominated for a global award or the People's Choice Award, between now and the 29th, you must upload a 30-second video to your project page. You have all that time up until then to modify your project page, upload new content, modify it, make it as good as you can make it. I would love to see our event get a global prize. Yeah, I think we have some very worthy contenders here. And of course, we'll hope to see you guys all back next year. So, with that said, guys, we have snacks outside.
Yeah, thanks.
So, you can go enjoy yourselves, have some snacks, relax, get a nap if you need it. As soon as the judges tell me we're ready, we'll just reconvene back in here and we'll You guys can go back to the work. And I think you're allowed to call people to have additional questions if they Yeah. We're still on, by the way. Okay.